thank you. I do apologize in advance because what I'm going to provide is some very basic advice, basically common sense. So if I say too many trivial things, please bear with me. But the idea is I'm going to discuss a little bit how to properly use the astrometric data Leonard has been presenting. And that would be our ideal case to work with any kind of data. We would like to have error-free data, or at least with errors so small that we could neglect them and assume they are not there. So no biases, no random errors, no correlations among pieces of data. We would also like to have a complete sample of all the objects representing the population we are treating. Or at very least a representative sample, which is the second best, but also very difficult. So no censorship, essentially. And also, we would like to have direct measurements of the quantity we are working with, and not a measurement of another quantity which we have to transform to our quantity to work with. And no assumptions about those transformations. So we will never have that. Not even in our dreams, we dream with having error-free data because this is simply not possible. So, we have in this, or Leonard has been discussing about biases. Biases is essentially when your measurement is systematically too large or too small for, with respect to reality, a reality we would never have access to. For the DR1 parallaxes, has already been mentioned, we have some 0 points. So globally, the Gaia parallaxes are slightly too large, slightly too small. From the validation work, we have found a possible value of minus 0.04. So parallaxes are have to be slightly corrected. I'll discuss about that later. But this is the order, 0.1, no more. There are also color-dependent correlations, color-dependent and spatially correlated systematic errors at the level of 0.2 milliarc seconds. And over large scales, we have to assume that there could be variations in this 0 point globally. This is small, but locally could be as large as 0.3 or more. Because in a few small areas of a few degrees, these variations of the 0 point can go up to 1 milliarc second. More about that in a moment. And in addition to that, we may have specific problems in a few individual cases, so specific biases for specific objects. All this sounds very, very bad, but it's not that bad. Okay. This is an example of the estimation of the 0 point from QSOs. It's essentially similar to the figure that Leonard has presented, but presented in a different way for northern and southern ecliptic latitudes. As you see for quasars, the number is quite small. And this is from the CFITs. We are also getting very small 0 points globally. Okay. But if you go zonally in regions, this is already seen. Leonard has already shown this split field of view. So comparing half of the focal plane with the other half. So as you can see, depending on the region, you might have variations between one solution or the other of 0.3 in one sense or the other. So this is the level. Our parallaxes can be, depending on the region, slightly too high, slightly too small. This is another figure not shown before. This is from the validation work from the CU9 work package devoted to validation. Sorry, I'm making a lot of noise here.
Maybe take off your badge.
Oh. Let's see if it's better. Okay, this is a comparison with quasars showing that originally, for instance, here, -1, or around here, +1, we can have a systematic local 0 point of the parallaxes that can be somehow large. But for most of the sky, this is good news, for most of the sky, the values are, again, very small. But be aware that if you happen to be in one of those regions, you might be unlucky, and your parallaxes might have a bias or significant bias. Okay, what can we do about that? I would say first it is okay to not introduce any 0-point correction. Or if you wish, you can, this is a value suggest, you can introduce a very small one. But at this point, we cannot say what is better. We suspect this is a value which should be subtracted. But if you don't do that, it's equally better. Again, with the R1, we cannot do better than that. But if you want to play in the safe side, could be okay to subtract this value from all your parallaxes. But what you cannot do is correct the regional features. As Leonard has already said, if we could do that, we would already have done that. Do not go to the previous map, say, oh, look, I'm in this region, let me add or subtract 0.1 milliarc seconds to our parallaxes. Because you could even do things worse, you could make things worse. In addition, for most of the sky, you have to be aware that you have to assume an additional systematic error of about 0.3. Your error cannot go below this value. So, as pointed out in the paper describing the release, your parallax has to have the error given in the catalog, but you have to take into account a 0.3, additional 0.3, a systematic one. How to treat that in a moment. And be aware that for those small regions that I have shown in the previous map, you can have even larger systematic errors. So, more specifically, when you are using a single individual parallax, okay, the suggestion is to take the formal error, the one given in the catalog, and add 0.3 in the quadratic way, proper way. So you have a total individual error which is larger by this quantity with respect to the one given in the catalog. This is to play in the safe side. Probably we are overdoing it. The formal errors already contain some margin, and this is a kind of worst case on average. It could be even a bit small in some specific regions, but on average for all the sky, this is overdoing it a little bit. But if you want to really be on the safe side, do not simply take the formal errors in the catalog, add this quantity to them for one parallax. Also check, as already discussed by Leonard, the astrometric excess noise to have an indication if there are potential problems with your specific star, indicating that could be a binary or that maybe in this region you have some problem with calibration.
Xavier, can I get interruption here? For the clusters, we find that that level is around 0.25 milliarc second.
0.5, okay.
0.25.
2.5.
So we do get below the 0.3.
Okay.
Yeah.
But for clusters,
so when I compare the Hipparcos cluster parallaxes with the Tychus cluster parallaxes, I need an excess noise of the level of 0.25 milliarc seconds to make the two sets agree. Yeah, not 3 milliarc seconds. So we do get below the 0.3 milliarc seconds.
okay.
Yeah.
But this is a kind of worst case.
Yeah, but if you say the global error will never go below the 0.3 milliarc second, I think it does.
Okay, again, I was getting here.
Yeah.
Again, we are playing it safe.
Okay, but
Probably.
in the cluster paper I will show that it's down to 0.25.
But cluster paper is specific regions of the sky. So
True.
in the rest of the sky, you can have cases where it's worse. So for a global recipe, a global advice on what to do if you don't want to take more specific.
Global advice does not contain the word never.
Okay. Should never go below 0.3. The idea, what I wanted to stress here is that if you take a group of stars and you average the parallaxes of those stars, you will be limited by the systematics. This will average out at the square root of n, but this will not. So you can reduce, when averaging groups of stars, this contribution by adding more and more objects, but this will stay there. So the suggestion is to keep as a global recipe a minimum error of 0.3 bands when you are averaging stars. If you are doing a specific work like floor, okay, you will know better than that. But as a general safe recipe, keep at least this 0.3 mass when averaging parallaxes. And again, do not try to get a zonal correction from the previous figure because it's too risky. You may be making things worse than they are. Okay, for proper motions and positions. In this case, the Gaia data is the best available by far. And we do not have the means to check, to do checks, validations as precise as the ones done for parallaxes. But in the margin of error, we have no indications of any significant bias. When you compare with Tycho 2, this is what you get. But those zonal fringes, those frames, well, so those strips are likely or almost surely due to Tycho 2 and not to Gaia. So for proper motions, I think it's safe to assume that we do not have significant bias, but be a bit careful about that. And as a general message, wait for DR2 where things will be even better. One thing I forgot to add here is about positions. Positions are also very good. No special indication of biases, except maybe some, when comparing with the ACRS, some residual rotation, but very small. But here, the problem would be that if you want to compare positions with other catalogs, you will have to do an epoch change. You can properly do that when you have proper motions, but then you have to propagate the errors accordingly. And when you do not have proper motions, you cannot properly propagate to another epoch. So you will have to take into account a larger error when comparing your position, Gaia position with another position. But probably Gaia position will be far better than any other position from ground catalogs. HST probably will be a different issue. Okay, random errors. Random, yes?
On proper motions, can't you? Okay. On proper motions, can't you look at the quasars, which you expect for physical reasons to have near zero proper motion?
Yeah.
That's like 500,000 million sources.
Problem with quasars is that in the solution, correct me, Leonard, if I'm wrong, it was assumed that they have zero proper motion.
In the auxiliary solution, but not in the main solution, was my understanding.
Yeah. You mean?
Can you go to the main solution, not the auxiliary, and look at proper motions of quasars?
Mm-hmm.
That one was done with Gaia. It was not a Gaia solution.
Not enough. So. Okay, for random errors, you know, your measurement is randomly distributed according to some PDF around the true value. So each measurement in the catalog comes with a formal error, and those errors indicated by Leonard for the astrometric solutions are quasi-normal. So the formal error can be assimilated to the variance of a normal distribution around the true value. And as already discussed again, the formal errors might be slightly overestimated. Some considerations. This is a comparison of TIGAS minus Hipparcos parallaxes. One would expect this comparison to follow this line if both errors were normal. But as you can see, there's a deviation at the tails from normality. Well, this is TIGAS versus Hipparcos. You cannot be sure why this deviation or where this deviation comes from, Hipparcos or TIGAS, but take into account that it might happen that beyond 2 sigmas there are more objects than expected from a pure normal distribution. So you will have outliers if you assume that the distribution of errors is fully normal. So objects that are beyond what they should be. But again, this is Hipparcos versus TIGAS. Could be one or the other or both, but at least take into account that you can have some 2 questions.
Has this been selected on solution type in the Hipparcos data?
This figure is from Leonard. Leonard?
have to check the paper to answer the question.
Is it possible that some of those outliers are really just astrophysical outliers, maybe binaries that could not be detected on the time scale of Parcos, and then there really is no, I mean, it's not due to either catalog, it's just the way the world is?
It could be, but then they would also be present in the TGAS solution. But the point here is that you might have more deviations from the true values that are larger when you expect from a normal distribution, either from astrophysical reasons or either from problems in the solution. Just a small one. There are not many, but be aware when doing some very extreme analysis that extreme cases might be more frequent from what you would assume from a normal distribution. Another warning is about the usage or comparison of data. This is the warning is about when comparing parallaxes from TGAS with other sources of parallax. This is an example. This is on the horizontal axis is Hipparcos value of the parallax versus the difference between the TGAS parallax and the Hipparcos parallax. The distribution has this shape, and one could think that there's some kind of bias for the small parallaxes. While in fact, this is exactly what you expect from the fact that the error in Hipparcos is larger than the error in TGAS. So this slope here, this apparent deviation versus large values here is exactly what you would expect. And in fact, this is a simulation with similar parameters than their true data, and you can see a very similar effect. You can see this deviation versus large values here. So the warning is because if you are not careful or you do not take into account the properties of the error distribution, you can make mistakes. And this is a suggested example. This has been published in our archive. This is a comparison of parallaxes from ecliptic binaries versus the difference between Gaia, or TGAS, and ecliptic binary parallax. And the author suggests some systematic or detection of some systematic effect from the fact that this comparison has some slope. While a simulation of the same situation gives a similar slope just because of the properties of the distribution of the errors. In the case of the Hipparcos parallax, the error is normal, while for photometric parallaxes or parallaxes coming from this ecliptic binary method, the distribution is rather log normal. So overall, the different distribution of errors gives an effect like this. So this is a warning on the comparison of sources of parallax, especially in this case, photometric versus trigonometric parallaxes.
10 minutes.
Correlations. Sorry, we have correlations in our quantities. Correlations is when a measurement is not completely independent from another. The 5 astrometric parameters have correlations. They are not fully independent, they come from a common solution, and the 10 correlations between these parameters are provided in the archive. It's a field called like parallax declination correlation, etc., etc. Essentially, the correlation matrix is given. How to interpret this? So this is, in 2 dimensions, an example of correlation. The quantity y, when taken alone, is normally distributed. Quantity x, when taken alone, is normally distributed, but when you look at them together in this plane, you see that the distribution of the point, the joint distribution is an ellipsoid, which has an inclination. When this happens, a situation like this means that if the deviation of measurement in x is positive, the deviation of the measurement on y tends to be also positive. So one error is not independent of the other. So for instance, if your measurement in y is truly has a 0 error, the measurement in x has a distribution exactly distributed around the true value. But if the measurement in y is larger than the true value, your measurement in x will be distributed around also a larger value. This has to be taken into account, especially when you use more than one astrometric parameter at the time. Typically, the case where this is relevant is calculating transversal velocities or space velocities, if you have a radial velocity, for a set of stars. The dispersion of velocities that you get will be the composition of the true dispersion of velocities plus the effect of the error. So to obtain the intrinsic dispersion of velocities, you have to subtract the contribution of the observational errors. But to do that, you have to take into account that the error in distance and proper motion in alpha and delta are correlated. Otherwise, you will be overestimating the contribution of the errors into the dispersion. So this is a warning and an example. And take into account that in DR1, the correlations might be large. As you can see, this is the parallax proper motion, right ascension correlation. One would like or would expect the correlations to be around zero, but notice that there are a large fraction with very large correlations. Even worse, they are spatially distributed in a very inhomogeneous way. Here you have a very positive correlation, and here you have a very negative correlation. Take this into account. In this release, still we have these problems like this. In future releases, we expect the correlations to be concentrated around zero. Censorships. Okay. We would like to have a complete sample, or at least a representative sample, for a given purpose. What's complete for one purpose might not be for another. DR1 is very complex data set, has already been mentioned, has been submitted to several combined censorships. The completeness of representativities cannot be warranted for any specific purpose. This will improve in DR2. So be careful when your application when your usage of the Gaia data might depend or might be conditioned by the completeness of the sample. This is the distribution in the sky of the TIGA solution, and notice that there are strips coming from the scan law and other artifacts. This is the number of good observations along the scan. Since TIGAS was selected in part based on the number of good observations, the completeness will be different depending on the region in this complicated way. This is another example. Due to effects of crowding, the completeness in a dense field might be different than the completeness in a sparse field, etc. There are many things like that. But the message is, it's very difficult to take into account all this, but you at least should try to take this, estimate the effect of this incompleteness for your problem. For instance, at least doing some simulations. But most important, do not make things worse by adding your additional censorships, like removing negative parallaxes or selecting subsamples on relative parallax error. And also, always use fitting methods able to use all available data, like Bayesian methods, and always work in the observable space. An example, quick examples. This is a simulation, a complete data set with errors of 2 milliseconds. This is the distribution of the parallaxes of the simulation, and this is the true parallax in milliseconds with respect to the TIGAS-like, well, it's not TIGAS, it's, the errors are a bit large, but TIGAS-like parallaxes. This is the distribution of true versus observed. The average difference of parallaxes is marginal, it's around zero, because this is the way the sample has been simulated. But if you remove the negative parallaxes, first, you are biasing the U distribution of parallaxes. You are removing more small parallaxes than large parallaxes. So now the average difference of parallaxes goes to 0.65 because you have removed a part of the distribution. Even worse, if you remove the parallaxes by a criteria of relative error, like here, sigma pi over pi larger than 50%, this is what you get for the complete sample. This is the difference between observed minus true as a function of the true. You are removing all these parallaxes here. This was usually known as a Lutz-Kelker bias. So first you have strongly biased the distribution of parallaxes of your sample, And notice that now the average difference of true versus observed is 2.2 mass. You have introduced a strong bias in your set of parallaxes. So please do never do that. Try to use other methods. Another example, if you truncate by observed parallax, this is what happens with the distance. This is another way of truncate biasing your sample. More about that in a moment. This is related to transformations. If you are not using, you're using or you need a quantity which is not directly observable, like the distance, but instead you're observing another quantity, the parallax, there's a transformation involved. A transformation, it's a bit of a problem because the transformation may change the behavior or the distribution of the errors in your quantity. For instance, a well-behaved symmetrical error in parallax might lead to an asymmetrical error in distance. Can lead to negative or very large values due to the shape of the distribution. This is a well-behaved distribution in parallax, and this is the matching distribution of errors in distance. Notice that first, the mode has slightly moved from the true value, the shape is asymmetrical, and there's a long tail towards large distances. This is what happens when you compare the true distance from a simulation versus the inversion 1/pi. This is the result of the tail here. So the distances, just by the fact that you have transformed from parallax to distance, are overestimated on average by 14 parsecs. Just the transformation gives you that. So how to take this into account? Avoid using transformations if possible. If not possible, use methods like ABM method or Bayesian methods that take into account all these effects in a natural way and provide unbiased estimates. And if possible, always estimate the remaining effect that might be there. And if, even worse, if you have additional assumptions about, for instance, about absorption, make sure that you put also these kind of assumptions or additional constraints into your Bayesian model, into your method for fitting. Thank you.
One or two quick questions and leave the rest for the discussion this afternoon.
Yeah, can you go back to one of your earlier slides? You showed Cepheids as a test. And I just had one question to ask you about those. I think it was very early. Much earlier. There. So here's an example, and maybe this is similar to what we found, where most of the points go through the error bars, and these are only random errors that you plotted. So what is your reaction to that? I mean, you talk about there must be at least a large systematic error in addition, but how would you, like on the plot on the right there, how would you interpret the too good chi-square?
Sorry, I'm not sure I get the question.
The chi-square is too good in general for a plot like this on the right, and you've only included random errors. So how does that leave room for a systematic error, or how do you interpret it?
Okay. This is part of the validation, and this is distributed over all the sky, and this would correspond to the global 0 point, which is estimated minus 0.04. This should be compared to the minus 0.04 that we get from validation, not to the random variations of all the sky. You see my point?
Yeah, but I'm saying, why is the chi-square so good?
So the
The error bars go through the line.
Yeah?
Too good.
It's not a 1 sigma, obviously, somehow.
You mean that the fit is too good?
Yes.
Ah.
And that's just random errors that you plotted. So I'm getting back to this issue of you're saying the correct errors are the random errors plus a systematic error that you should add, and already it's too good without the systematic error. What do you think?
Well, first, we have been overcautious, but you have also to take into account a figure like this. Sorry.
Yes, I think this is an interesting question which has a long answer. And I suggest that we take that up in the afternoon session.
Mhm.
Okay?
Fine.
Yeah.
Okay, take one more, and then we have to go to coffee.
So you may have said that, apologies if I missed it, but the plot, I guess, 2 slides down from this one, where you show, that one, no, previous one, where you showed his regional effects. So do you understand why is there spatial structure in here? Where does the spatial structure come from? If this is just a solution from one half of the focal plane versus another half of the focal plane?
A combination of many factors. The scan law, for instance, is not homogeneous. You have more observations in certain regions than in others. The fitting of the attitude might be worse in some places than in others, etc., etc. So this
But would you expect that to equally affect both parts of the focal plane? I guess I'm.
No, this specific one is, I thought you were talking about regional effects, but chromaticity is not affecting both focal planes in the same way. Leonard showed a figure about the chromaticity that has not been corrected, so the difference can come from this, but I'm not sure I'm getting the question.
Why does early versus late depend on where in the sky?
Yeah, that's basically the question.
Okay,
Well,
let's think about this and take it up again in the discussion. I think there's not unless you have a very straightforward answer.
Well, I think it's related to chromaticity because chromaticity is different.
Yeah, but the question is why do you then get a
I think here you have the galactic center where the stars are redder, and here's another part of the galactic plane with stars are redder. I think it's the distribution of the colors of the stars in each region.
Yeah.
Yeah, that's part of the distribution of sources of the sky in color.
On the focal plane.
So here you have galactic center, more red stars. The effect is in one way. Here also a part of the galactic plane, while here is outside this thing. This is the reason. But we can go back to this figure during the...
Yeah, let's come back.